the microwave-looking thing is what's called a power supply. It takes electricity given to me by the electric company and turns it into a measurable, actually a changeable current and voltage. I know we haven't got into circuits yet, but all you need to know is that from this power supply, there's a steady stream of electrons that goes out through this red cord and this way as it passes through the red cord, back then through this black cord, and then back to the power supply. So there's just a stream of electrons. When I turn the power supply on, there's a stream of electrons that goes around traveling this way. Does that make sense?
Yes.
Okay. So hopefully you guys can see up there what's going to happen. Now, what's going to happen is I have this magnet. Okay? This side is north, this side is south. Can you guys see that? Yeah, Julie, am I low enough for you to see it? Okay, I'll get a little lower. All right? So this side's north, this side's south. So I'm going to have this wire passing through this magnet. Okay, do you guys see it? Okay. Now, the wire is just sitting there normally. Okay, I'm going to try to, I'm not touching the wire at all. Okay? I want you guys to watch what happens when I turn the power supply on. You'll know the power supply is on because you'll see this the screen right here light up with some readings. Okay? So don't worry about what's on the screen. I want you to focus on the wire. Okay? Focus on the wire. Watch what happens to the wire.
Is it safe?
Okay? Yes, it's safe. Okay, you guys ready?
Blow up.
3, 2, 1. What happened to the wire? 3, 2, 1.
They go down.
It goes down. You guys see that?
Yeah.
So Mr. Branch is the magician, right?
Oh.
Okay. What's happening is the magnetic field, right? This is a horseshoe magnet, right? So the magnetic field points from the north to the south. So within that horseshoe magnet, there are straight field lines. Those field lines are perpendicular to the direction the electrons are traveling, right? So since the field lines, the magnetic field is perpendicular to the electron's direction of travel, the electrons feel a force. And that's indicated by the wire doing what? Moving. Kind of cool, huh?
Wait, so you talk about the perpendicular. So what is perpendicular with each other? The electrons and the magnetic field.
Yep.
And the electrons in the wire.
Yep.
Are perpendicular.
Yep. The motion, the path the electrons are traveling is down this wire. So it goes this way, right?
Yeah.
The magnetic field points from north to south, so it's going this way. Okay?
Okay.
So it's like I have one going here, one going here, and one going here.
Okay.
Okay? Like one's going this way and one's going that way.
Mm-hmm.
Alright? Does that make sense? Now, little prediction time. Right now, north was close to you, south was away from you, right? Right, Amina? Okay. I'm going to turn this around so that south is close to you and north is away. Now, the wire moved which way the first time?
Down.
Down. So which way, think for a moment, which way is the wire going to move now?
Down.
Okay, who thinks they know? Lynn, you say down?
Yeah.
Anybody else? Derek? Down?
I'll go up just to be that guy.
Kevin says up to be that guy. Sergio?
No.
Down? Anybody else? Okay, who says down? Raise your hand. Who says down? Who says up?
I'll be that guy.
Who says nothing happens because I messed with the situation?
That's probable.
Okay. Okay. That's probable. Are you guys ready? 3, 2, 1.
Oh, I was that guy.
Which way does it go?
Go up.
I was that guy.
Oh, no.
You were there.
Oh.
So, what's happening?
It doesn't like it.
Okay. Based on the way the field lines point and the direction the electrons are going, the force felt is different, right? In one case, the force is up. In the other case, the force is down, right? So there's kind of a rule here that's governing the situation, right? There's a rule that's affecting this, right? Are there any questions, any more demos you want to see before I jump into some notes about this?
If you put
What happens if
Yeah, what
Yeah,
happened to the
horse.
strong magnet?
What?
What happens if you did the strong magnet?
The bullet
instead of
Oh, that is the strong magnet.
No, the
that one? No, the little one that you.
Oh, the little bullet one?
Yeah,
The
one
problem
that-
with that little bullet-looking one is the little silver magnet does not have straight field lines, right?
So what would it do?
So it
Well-
wouldn't work if it wasn't.
The reason why this works is because we have so many straight field lines. So we have so many straight field lines in between here, Kevin. Okay, that the forces all add together. Think about how vector addition, right?
Yeah.
if my field lines were curved, then the force felt by the wire wouldn't all be in the same direction, so it would not deflect as much.
Would you be able to see it though?
I haven't even tried it because usually you can't get straight field lines around it. Okay. The nice thing about a horseshoe magnet is in here we have straight field lines and they're really dense. The field lines are really dense in the middle, so you get a really strong magnetic field. So even though that little bullet magnet is a stronger magnet than the horseshoe magnet, inside the I guess the legs of the horseshoe magnet, you have a stronger magnetic field than you do around the bullet magnet. Okay?
So Mr.
What do
Branch,
you do with the bullet
it doesn't
magnet?
matter if you turn the
School supply stuff. What?
So it doesn't matter if you turn the magnet around.
Nope.
Okay.
We still get a force.
Yeah.
The direction
But
of the force is different.
Right.
Okay? The direction of the force is different.
So
Okay.
So can you predict,
Can we predict?
like, if you turn it that way, it will go to up or down or?
Okay.
Yeah.
Well, let's draw a picture. So, any other questions there, demos you want to see real quick? Okay. What'd you say, Moses?
you said Brand got some big biceps though.
When you zoom in on them. Okay. So, force felt by charges moving through. This marker is terrible. So you can make it? No, I'm not going to try it. Mike goes in the way. Okay. So force felt by charges moving through magnetic fields.
That's some nice,
Okay.
some nice texty language there.
What do you mean? Through?
Through.
It's in the dictionary. Okay. So we had a horseshoe magnet, right? Here's the horseshoe magnet. So north, south. Which way does the field lines point? From north to south. Right? Okay. And in one instance, if this is my wire, okay, and current is coming through the wire so that current is passing through the wire, right? The wire felt a force which way? Okay. Where in this case the wire actually felt a force up. Okay, force was up. Now when we flip the bar magnet around, or not the bar magnet, the horseshoe magnet around, the field lines are going the other way. Current still went the same direction, right? So in this case, the wire felt the wire felt a force which way? Down. So force was that way. Down. Okay. Now, I think I said it earlier, but what is current? What is current passing through the wire? Electrons. Okay. Current is electrons moving through a wire. Okay. Current is actually measured in amps, and amps is coulombs per second. Coulombs is charge, right? Right? Charge per second. So that's what current is. Current is electrons moving. All right. Any questions about that? No questions?
Wait, Mr. Branch, how do you know which way is the force?
Which way is the force?
Yeah.
Okay, we'll get to that.
Okay.
Okay.
All right.
So, any questions about what we observed? Kevin, Tim, what's going on here? Hey, 11 days left. Doesn't mean we just sit here and do nothing. All right. There's 11 days to do something. All right. So, these charges, guys, these charges feel a force. Now, did the direction of our magnetic field affect the way the force felt was? Did the direction of the magnetic field affect the force?
9.
What do you think?
9.
Oh, I don't know.
It affected how it moved, right, Shelby? when I flip the magnet around, right, the wire moved the opposite direction. So does the direction of the magnetic field affect the force?
Yes.
Yes. The direction of the magnetic field affects the force. Okay? Does the... If I had a stronger magnetic field, what do you guys think would happen?
It'll go deeper or higher.
Okay, good. The force would be larger, right? If we had stronger magnetic fields, the force would be greater. Okay. Now, the equation that kind of governs this situation is this one right here. F equals Q V B.
Yay.
Okay. Q V B. Okay. What is Q?
Quantum
The charge.
mechanical physics.
Charge. Okay. That's in coulombs. What is V?
Vanilla ice cream.
Okay. Velocity. Yes, Kevin.
Are we gonna be like Sheldon's when we're done with this class?
I don't think so. He's pretty smart. Okay. What is F?
Not in real life.
What is F?
Force.
Force. So the one thing we're missing here is what?
B.
B. What do you think B is?
Buttercup.
Ah. Kind of hungry. I showed you.
I'm hungry, I know.
What is B?
I can't believe it's not.
What's the one thing I didn't account for? We talked about a force, right?
Butter.
The current is my charge, right? The velocity is the rate it's moving.
Wait.
So what do you think the B is? What's the one thing we didn't talk about yet?
Magnet.
Magnetic field.
Oh, I'm over here thinking of things that start with B. I'm like, I'm like,
Don't worry, sir.
Okay. B is the magnetic field, and it is measured in Teslas.
Teslas?
Teslas. Right?
Tesla.
Now, if I look at the situation I have here with the wire passing through the horseshoe magnet, okay? What's the relationship between the velocity and the magnetic field?
The relationship between velocity and magnetic
Yep,
field.
the velocity of the charges.
The greater the velocity,
Remember-
the stronger the magnetic field.
Okay, I'm talking about like orientation, just directions. So the magnetic field went like this, right? Right? The charges came through this way, didn't they?
Mhm.
So what's the relationship between those? They form what type of angle?
Perpendicular.
The perpendicular, right? Now, how does the force compare to the velocity? So when we had the wire, so if this is my horseshoe magnet and the wire is going this way, which way is it? Where the charges are going this way? Which way do they feel a force?
Parallel.
No.
They feel a force up or down.
It's in the middle.
So how is that force compared to the velocity? What do you think? Perpendicular, right? Velocity is coming at you. The wire feels a force up. That's perpendicular, right? How does the force compare to the B field, the magnetic field? It's perpendicular. How is velocity compared to the magnetic field? Perpendicular. Okay? So in order for this equation to work, all of these quantities, all the vectors there, the force, the velocity, and the magnetic field, all have to be perpendicular. Okay? So F, Q, and B, F is perpendicular to Q, Q is perpendicular to B, and B is perpendicular to F. They all have to be perpendicular. If they're not all perpendicular, this will not work. Okay? Then the
Wait,
charge
Mr.
will
Kevin,
not feel a force. Yes,
I
Lynn?
thought you said that velocity is perpendicular for each of them, so shouldn't it be parallel?
Nope.
No.
You're probably wondering, how can I have three things be perpendicular? Right? How many dimensions are we working in?
11.
3 dimensions.
Is it true that
Okay.
there's a fourth dimension?
So, if you count time as a dimension, that's fine. So what that means is if the velocity is this way, okay, and our B field, magnetic field is that way, right? Then which way does the force have to be? Either
Down.
towards you or
Away.
away. Okay, you guys talk about the z-axis? So B field, force, and velocity, they all make right angles.
Oh, X, Y, Z.
Okay, X, Y, and Z, like the X, Y, Z axis. Okay. Now, you are equipped with an X, Y, and Z axis. Every one of you is.
I got it.
You know how I know? Because every one of you has a right hand. Okay? Your right hand is an X, Y, Z axis.
So if we were
Okay.
without,
See, look.
what if we were born without hands?
Yeah.
Well, I looked before class started.
But like, what if we weren't? Then we wouldn't.
But I looked before class started, so we don't have to worry about that.
What
Alright.
if it was
So,
okay?
your right hand, Julian, thank you. Your right hand is an XYZ axis. Okay? Depending on how I orient my hand, my middle finger, my pointer finger, and my thumb, sorry.
How are you doing that?
Make it like a gun.
Alright, done.
Okay? Then take your trigger finger and just straighten it. Okay? So now I have an X, Y, and Z axis. Does that make sense? Now, this X, Y, and Z axis, this is important for this equation because my right hand can tell me which way a charge feels a force based on the velocity and the B field, the magnetic field. All right? The way you remember it, all right, is if I'm shooting a gun, if I'm playing cops and robbers and this is my little gun, right? Which way does the bullet go? Out of the pointer finger, right? So that pointer finger is my velocity vector. Because that's where the bullets have velocities. Does that make sense? Okay. Now, the other two are pretty easy to remember. My thumb is for the force. Thumb, force. I'm saying it wrong intentionally. Okay? I know it's my thumb, but my thumb has the force. You got that? And my bad finger, okay, only works in America. My bad finger is the
Force.
magnetic field, the B field. Okay? B for bad.
Oh.
Okay? Thumb for force. V for velocity, because that's the way the bullets go when I shoot my toy gun. Does that make sense? So, velocity is your pointer. B field is your middle finger. And your force is your thumb. Okay? Does that make sense? Alright. Now, I'm going to draw two quick pictures here. Okay, I know I don't have a lot of time left, so please bear with me, guys. Okay. What?
Earlier, we're being taught when you said school should teach.
Alright, so here we go. Guys, I have horseshoe magnets again. You guys see the horseshoe magnets?
Yeah.
Okay. The lines pointing to the left, from left to right. Those are my B fields, right?
Yes.
Okay. Now this circle and that X, those are my velocities. Now think about it. If someone is shooting an arrow at you, do you see an X or do you see a point?
I see a point.
You see a point. That's what this is. It is a point. It's a point coming at you. So this velocity is coming at you. Okay? If someone's shooting an arrow away from you, what do you see? The X, because you see the feathers on the arrow, right? So vectors are arrows. This is a vector going away from you because you see the feathers of the arrow. Okay? This is a vector coming towards you because you see the point. Does that make sense? Now let's figure out the force felt by this wire or that wire. Okay? These are two wires with velocities going in different directions. So on this one, the B field is my bad finger, right? So I got to put my bad finger in the direction of the B field. My pointer finger is my velocity, right? So my velocity is towards you. Which way does my thumb point?
Up.
Up. So which way is the force?
Up.
Up. So that's the force. Okay? Now I go to the other side. Bad finger, right? Velocity in the board. So bad finger's pointing that way, velocity's in the board. Which way is my thumb? Down. So this one feels a force down. And that's why the wire went two directions based on how I had my magnet set up.
So is it like arrow reverse and watch it go up and then